Good day. We're going to talk about torque here a little bit today. And so there are references here to culturally important references. The power of the torque and your torque is R cross F. You'll just have to wait if you don't know what those are about. All right. We want to do two things with torque, and that is we want to learn what it is and what does it do. We'll do the first one first. What is torque? It's a defined quantity, and here's how it's defined. It has to do with force, but it isn't just force. So let me give you a specific context. Suppose you have a stick. So I will draw a stick, and suppose that this stick is pivoted at some point. Like here, this is an axis, so it's allowed to rotate about that axis. Suppose then that someone exerts a force on this stick. We have, of course, drawn many free body diagrams this year, but we've been treating everything as a particle. And what that means is when we've done free body diagrams, we've said, okay, here's an object, and we've drawn forces on the free body diagram, and we haven't really been concerned with where we draw them other than that they're on the diagram, because we've just been interested in whether this thing accelerates or doesn't accelerate. And again, we've just been treating everything as a particle. Now that we're interested in looking at whether things are rotating, if they do, does the rotation increase or decrease? Do they have angular acceleration? We're interested in where these forces are applied relative often to some axis of rotation. So I go back to this stick. It's pivoted at some axis, and someone exerts a force on it. And I'm just going to invent just some magical force, F. And it's applied here, and it's of a magnitude F. And the way I put this is, I ask myself, does that force create a torque about that axis? That's how we use the terms. The force isn't a torque. The force can create a torque about that axis, relative to that axis. The other relevant bit of information we need then is how far is it and in what direction is it from the axis to the point of application of that force. So I'm going to draw this new vector, and I'm going to label it R. And that is the direction and distance from the axis of rotation to the point of application of force F. Now that we know those two things, the torque created by that force is defined as, first of all, the symbol we use is a Greek letter tau, small case tau, I believe, and it is equal to the magnitude of R, which is a vector, and we're going to actually get into the vector nature of this stuff in the next chapter, but for now, it's the magnitude of R times the magnitude of F, the magnitude of that force, times the sine of phi, and I haven't defined phi yet, so let me do that. If I take these vectors and redraw them tail to tail, now of course with the magic of smartboard technology I can move everything except the vector. Okay, if I redraw them tail to tail, let me move these, this is going really smoothly, like that, ta-da. The other thing I could have done is, of course, is just because I'm basically doing a sketch here, so I could have just attempted to redraw them off to the side somewhere. Here's R, more or less. Here's F, more or less, drawn tail to tail. Okay, the angle phi is the angle between these vectors when drawn tail to tail. I've now drawn them twice. So, if I go back to the original drawing, that looks something like this. Notice that phi is not the angle between them when drawn in the drawing. No, the phi is the angle between them when drawn tail to tail, which is not how we draw them when we're actually analyzing the force on the stick, which means you have to redraw them, which we did. All right. Phi also can be drawn, by the way, if you might notice that if you simply extend the line that of this distance from the axis to the point of application of F. If you extend that, phi is the angle between F and the extension of that line. Okay, so there, ta-da. That's the definition of the torque created by that force relative to that axis of rotation. All that stuff has to be included. Let's see a couple things about what happens when we find a torque. For instance, let me just make up some numbers so we can see how the units work out, because there's one kind of interesting thing about the units. If that distance r happens to be 2 meters, and if the force F happens to be 10 newtons, and if phi happens to be 30 degrees, which it isn't, but I know the sine of 30 in my head, so I'm going to put 30 degrees there, then the torque in this case is 2 times 10 is 20 times sine of 30, which is 0.5, and I get 10, I think. The point here is what happens to the units. It's newtons times meters. Newton times meters. And I'm going to say something about that, and that is that you might say, oh, Newton meter, I've seen that before, that's a joule. We do not call this a joule, which is kind of odd. It's dimensionally the same as a joule, but it's not the same as a joule. This is not a unit of energy. And torque isn't the same quantity as energy. It's dimensionally the same, but it's not the same. So at some point, maybe in 2 minutes, maybe in 2 days, I'll get into a little more detail what I mean about that. But for right now, don't write joules. It ain't. It's newtons times meters. So, okay, units of torque. And it is, again, defined as the distance from an axis of rotation to the point of application of force times the angle between those vectors drawn tail to tail. Let's just do a couple of other quick examples to see how we calculate torques. Let's look at an example from class today when we had the stick that was that we pivoted and then we released it as a pendulum sort of thing. I might be interested, I might say to myself, what are the torques on this stick when I release it from, or even before I release it, from this, from being held up by that pin that it was held up by. So this is the pin, this is the axis of rotation. What I want to get at here is how do we deal with the torque created by the force of gravity. So let's in fact say that I'm holding this up, so I've got my finger under the right-hand edge before I release this stick. So I have, if I actually look at the forces on the stick, I'm holding it up on the right-hand side with my finger, so I have some normal force there. There's also an upward force exerted by the pin that this thing is hanging from. I'm going to call this F subscript X for the axial force at the axis. And that's because the pin is supporting it. And the downward force on this thing, not that there has to be one, but there is the force of gravity. Now here's the fact. The fact is that the gravity acts on every bit of stickness in this stick. Gravity doesn't act at a single point. Gravity is a force between mass and mass, and the stick has mass everywhere throughout the stick, and every molecule of stick, the molecular form is woodium. Every molecule of woodium is pulled down by gravity. I'm not going to put those 6 bazillion little force vectors on here. What I will do is I will treat the gravitational force as acting at the center of mass, which is in the middle of this stick. And so when I draw the gravitational force, I draw it at the center of mass, and I can treat that force as acting at the center of mass when I'm calculating torques. So in this case, then, if I were to say there's a free body diagram of the stick. Remember, this is before I release it. So the stick is suspended there, held up by the axis on the left, the pin, and by my finger on the right, and pulled on by gravity. Which of these forces create torques? Let's talk torques here for a little minute. Well, there are 3 forces, and I can speak meaningfully of the torque created by each one of them. What is the torque at the axis? What is the torque created by the gravitational force? And what is the torque created by the normal force? Each of these forces creates a torque. Let's apply the general definition, Rf sine phi, to each one of these. Okay, the first is the upward force exerted by the pin, what I'm calling Fx, the force at the axis. If I write this general formula, Rf sine phi, if I then plug in the relevant values, Well, what is r? R is the distance from the axis of rotation to the point of application of the force. This force is applied at the axis of rotation. Since r is equal to 0, I'm going to get rid of this equal sign. The whole r is equal to 0, which I'm going to write somewhere. R is equal to 0 for this first force. The torque created by the force is 0. I arrow 0 the whole thing. So the force exerted by the pin on that stick, exerted at the axis, creates no torque. There's a force there, but it doesn't create a torque because r is equal to 0. Okay, next, the gravitational force. What is the torque created by that? Well, this certainly, what colors do I have left? Green. This certainly doesn't act at the axis. There's a distance r for, I'm going to give the subscript g, the distance from the axis to the point of application of gravity where we're treating it, the center of mass. So this time I write r, for r I'm going to put an rg, and in the experiment that we did today, this happened to be 0.3 L, 30% the length of the stick. So I can put in here 0.3 L for r. The force is Fg, or it might be useful to write m times acceleration due to gravity for the force. And sine phi, in this case, the angle between r and Fg, if I redraw them off to the side here, from a common origin, draw tail to tail, there's Rg, there's Fg, and that's a 90-degree angle in there. And so this is going to become sine of 90 degrees, which gets arrow 1. And so the torque created by the gravitational force is 0.3 mgL. Again, you might notice, oh, that looks like a potential energy. It isn't. It's not. It has nothing to do with potential energy. MgL looks like energy. It isn't. Finally, the normal force exerted by my finger creates a torque. I'm going to plug in R times F times sine phi for this particular force. R for this force, the normal force, I can call it R subscript n. In this case was 80 centimeters or 0.8 L. And so I would say it's 0.8 L times the normal force. And again, if I'm exerting this force straight up, this time I'm going to extend that line of Rn. The angle between Fn and Rn is 90 degrees. And so I would again say sine of 90 degrees, which is arrow 1. So in this case, I get 0.8 Fn times L. Okay, so there's some torques. Okay, we've been calculating the magnitudes of torques. What about the directions of torques? Torque is a vector quantity, he says, slowly and emphatically. For the time being, we're going to treat the direction of torques. It's kind of lame, but we're going to do it during Chapter 9. The same way we've been treating the direction of angular velocities and angular accelerations. And that is, we're going to look at the page we're drawing on and say, is the torque clockwise or counterclockwise? And what that means is, and it is what it is. What I mean by is the torque clockwise or counterclockwise is this. Would this torque acting by itself tend to make this stick rotate clockwise or counterclockwise? So you have to kind of visualize here. The gravitational torque, the torque created by the force of gravity, if you imagine this stick and it's pivoted where the axis is, and the force of gravity pushes down in the middle, it's going to make the stick rotate in the direction it actually did in our experiment, which in this case is going to tend to make it rotate in this direction, which is clockwise. And so I would say that the torque created by the gravitational force is clockwise. That's its direction. On the other hand, the torque created by the normal force of my finger pushing up on the stick, if that were the only force on the stick, which is still pivoted at the axis, that torque alone, the torque created by that force alone, would tend to make the stick go counterclockwise. So if gravity turned off all of a sudden, and I'm pushing up on the stick's going to rotate counterclockwise around the axis. And so I would say that the torque created by the normal force is counterclockwise. Now we've been using the convention that this is the positive direction and this is the negative direction. And we can continue to use that convention, but we should be aware of the actual direction of these torques. Okay. I think that will do for now for what a torque is. And the next thing is what a torque does. And I'm looking at the time, and I'm taking way too much time. Let's go faster. Okay, what does a torque do? A torque tends to make things have an angular acceleration. In this case, the torques on the stick are balanced, and the stick remains at rest, in other words, with no angular velocity. But the answer to the second question, which I'm going to write down here, 2, what do torques do? And this is very analogous to our discussion of forces with Newton's second law. An unbalanced force makes an object accelerate. Balanced forces, it either doesn't move or continues moving at constant velocity. An unbalanced torque, a net torque, will tend to cause an object to have angular acceleration. Whereas if the net torque is 0, that means that an object will have no angular acceleration, which means it'll either just sit there or rotate at a constant angular velocity. This is reflected in a formula which is often referred to as Newton's second law, because it is, where we say net torque is equal to I times alpha. This is analogous to Newton's second law for linear motion. Net force is mass times acceleration, where I is moment of inertia. That's a measure of resistance to angular acceleration, in the same way that mass is a measure of resistance to linear acceleration. And angular acceleration is angular acceleration, and A is linear acceleration. So they kind of match up with each other. Net torque is I alpha. So that's what torques do. They make an unbalanced torque makes something have an angular acceleration. I'm going to quit this. So I'm going to do a couple of examples in a separate video. So we're good.